Today we're going to talk about transformations of exponential functions, part 2. For this video, we're going to go over dilations, reflections, and then use transformations to identify exponential functions from graphs, and then write equations of exponential functions that involve transformations. The first kind of a dilation is a vertical dilation. This is happening directly on the y values. So the graph of g of x, which is ab to the x, is the graph of f of x with just b to the x. Notice the only difference is the a that's over here. Will be stretched or compressed vertically by a factor of the absolute value of a. So if the absolute value of a is bigger than 1, then the graph gets stretched vertically. If the absolute value of a is between 0 and 1, then it gets compressed vertically towards the x-axis. When we look at horizontal dilations, the graph of g of x equals b to the a times x. So now we're affecting the x value directly. That's the graph of f of x equals b to the x, so that's the parent function. It's stretched or compressed horizontally by a factor of 1 over the absolute value of a. So it's reciprocal. If a is greater than 1, then f of x is compressed horizontally towards the y-axis. If the absolute value of a is between 0 and 1, some kind of fraction, f of x is stretched horizontally away from the y-axis. The first example here wants us to describe the dilation of g of x equals 1/4 of 3 to the x as it relates to the parent function of 3 to the x. So the only thing that's added is this quarter right here. Since this function is being multiplied by a positive constant after this calculation is done, and this number is between 0 and 1, so 1/4 is between those two, it is being compressed vertically by a factor of 1/4. And one thing you might notice here is the y-intercept that started at 1, which is 0, 1, is now at 0.25 down here, which is a quarter as big as it was, which is causing all the values of y to get smaller in this direction, closer to the x-axis. Now we're going to describe the dilation of g of x that equals 5/3 raised to the 2x power as it relates to the function, the parent function of 5/3 raised to the x. So we're adding this times 2 directly to the x itself, which is the exponent. It's a positive number that's multiplied before you evaluate the whole function. And since the absolute value of a is greater than 1, the graph is going to be compressed horizontally by a factor of 1 over 2. So the f of x is going to be pushed inwards this way. So all the x values are going to get half as big, which makes them get closer to the y-axis. All the x values along our curve here are going to get half as big, which push them closer to the x-axis. One way to tell right here is this dot over here is 4, 7, and then it becomes this dot right here, which is 2, 7. So you can see the x value got half as big, making a compression. All right, so since 2000, solar PV capacity in the world has been growing exponentially. It can be approximated by the function of c of x is equal to 0.897 times 1.4 to the 46 to the x power, where c is the solar PV capacity in gigawatts. So c of x is the solar gigawatts, x is the number of years since 2000, and 0.897 is the initial capacity. Describe the dilation as it relates to the parent function. Well, c of x is really going to be a times f of x because we have an a value here. And since the a value is smaller than 1 but greater than 0, we are going to have a vertical compression here. And the reason it's vertical is because it's happening outside of the original function f of x. So f of x is completely calculated, then we times by the a value, which is smaller than 1, and it makes the y values become smaller, which is the effect of a vertical compression. Okay, so we want to identify the function from the graph. The given graph is a dilation of the parent function f of x equals 2 to the x. So that means 2 raised to the first power will give us this dot here on f of x, and 2 raised to the second power will give us this dot right here. So we got 2, 1, and 2, 4. But notice the g over here is, the dot that relates to it is actually lower here. So the graph appears to be a vertical compression. So g of x appears to be a times 2 to the x power. And since we have a dot right here at 2, 1, we have a dot at 2, 1 that was originally at 2, 4. So this was f of x, and this is g of x. It looks like the y value got 4 times smaller, so it looks like a is equal to 1 over 4. And one way we can figure that out is substitution. So we have g of x equals a times 2 to the x. We want to find out what the a value is. So the x value, we're going to substitute the x value in at 2, so 2 to the second. And then the output of g at that point became a 1. And we end up with 1 equals a 4 times a, because 2 to the second here is 4. And then we divide by 4 on both sides, and a equals 1/4. Okay, so here we have reflections of exponential functions. We've got two types again. We've got reflections across the x-axis, which are vertical, and reflections across the y-axis, which are horizontal. So the graph of negative f of x, so f of x has been calculated and then we times by a negative. What that is going to change is the y-coordinate is going to become the opposite. So every y-coordinate is going to be multiplied by negative. The next one is the horizontal, which goes across the y. So now we're multiplying by negative directly on the x. So all of our x values are going to become opposites first, and then we calculate the y's. So that's multiplying the x values by negative 1. So here we have our first one. It's a vertical reflection. So to describe the reflection, g of x equals negative 3 times 2 to the x as it relates to the parent function of 2 to the x. So what we have on the outside is a negative, which is going to cause a vertical flipping. But because the 3 part of it is greater than 1, it's also going to be a vertical stretching. So what's going to happen here, if I go to the original point here, which is 0, 1, the output of 1 is going to be multiplied by 3, so it becomes a 3 up here. And then when you multiply by the negative, so I multiplied by 3 first, and then when I multiply by a negative 1, which is the negative part of the 3, this number, this dot moves or flips vertically across the x-axis and becomes a negative 3. And our graph, you can see, then becomes steeper as a result of transforming that point vertically. So first thing we did is we multiplied it by a 3 to make it move up, and then we multiplied it by a negative 1, which flipped it across the x-axis. So our next one is a horizontal reflection, and we have 3 raised to the negative 2x power, and the parent function is just 3 raised to the x. So there's actually two things happening here. We're multiplying by negative 1 and we're multiplying by 2 directly on the x value. So multiplying by 2 is going to cause a horizontal compression by a 1/2 factor. So all the x values along f of x are going to get 2 times closer. So I got a dot right here at 1, 2 times closer will be a 1/2. And then if I multiply it by a negative 1, it will flip to this side of the graph. Same thing will happen with this dot here. It moves closer to about 1/2 and then flips to this side of the graph, creating the graph to look like that. Okay, so here's a rule that you could probably write down in your foldable. The general form of an exponential function, f of x, is going to equal a times b to the x minus h plus k, where a, h, and k are parameters that dilate, reflect, or translate the parent function with base b. So the only thing that's not going to be different from the parent function would just be the b value. The absolute value of a stretches or compresses, which is a dilation of the parent graph. When a is negative, the graph is reflected across the x-axis. The value of h shifts or translates the parent function right or left, and the value of k translates, which is a shift again, the parent graph up or down. All right, so here we have multiple transformations. So looking at this one up here, we have g of x equals negative 1/2 times 3 to the x minus 2 minus 1. So the parent function is just the b value of 3. Out front, we have an a value that's equal to negative 1/2, and that's actually going to do two things. The negative 1 part of it is going to be a vertical reflection. So it's going to flip vertically over the x. And the 1/2 part of it is a vertical compression, which is going to make it closer to all the points closer to the x-axis. So it's going to squeeze it together vertically. Then we have an h value at the top, which is the 2 there. And remember, we're going to do the opposite. So that's actually a positive 2. And what that's going to do is going to shift horizontally to the right by 2 units on the graph. And this minus 1 at the end is our k value, since that's a negative 1. That one's going to shift vertically down 1 unit. So if we trace a point on the graph, we can see what effect each of these points will have. So let's use the y-intercept at 0, 1. The calculation should be relatively easy there. First thing we want to do is all the horizontal transformations. So the horizontal is moving this thing to the right 2. So this thing moves 1, 2 to the right. Then we're going to times it by 1/2, the 1/2 here. So the y value becomes half as big. So now the y value is going to become half as big, so this moves down by 1/2. And then it's going to multiply with the -1, which is going to flip it vertically. So this now flips over the x-axis, which is right here, about half as big. And then we apply the k value, the vertical shift last, which is going to move it 1 unit down. So this moves 1 unit down. And you can see how it lands back on the graph. Now we have our sketch that looks like this, which is going to be vertically compressed, shifted to the right, flipped over the x-axis, and then shifted down 1 unit.